Okay, let's talk about the laws of the thermodynamics. We're actually going to start with the third law. This is a little bit easier to state. The second one I'm going to derive for you, and then we'll see the full extent of what it means. All right, so the third law of thermodynamics has to do with entropy. In particular, there's an equation that gets presented in books, and I'm going to show it to you, but I'll be honest with you. I will not actually be asking you to do calculations with it, but this is an expression of entropy based on the idea of a statistical distribution, in particular statistical distribution of energy states for canonical ensembles of molecules or energy levels. The point being that it can be rather difficult to address that in equation format because you have to consider a lot of states in the quantum chemistry realm. You have to consider the possibilities. You have to apply statistics to it, the permutations, commutation rules, and then do the entire calculation using usually Stirling's approximation just to get to a value of entropy. And so here I'm just going to show you, yes, you have probabilities associated with the W term, which is the statistical measure of your energy distribution. The value of Kb is not a rate constant, by the way, that's the Boltzmann constant, and it has the same units as entropy. And pretty much this is the relationship that Boltzmann created to kind of merge two realms together. On the one hand, you had the quantum chemistry realm, which is like the one atom or the one molecule, and then you have the bulk sample, which is the stuff that you actually handle that has like 10 to the 23rd or more atoms or molecules present in it. And so there is a little bit of a disconnect when you go from the nano world or quantum world to the actual, bulk sample world that we are accustomed to interacting with. But Boltzmann basically takes a jab at it and does a pretty good job of equating the probability aspect of quantum mechanics to ultimately the entropy of the bulk sample. And with this equation, one thing that does become kind of interesting and obvious is that as the temperature is decreased to a value such as absolute zero, what has to happen is that at absolute zero you have no kinetic energy whatsoever, like no energy whatsoever that is kinetic. And because of that, you don't really have the possibility or the option to occupy higher energy states. So the one thing that will have to happen if the temperature is at 0 Kelvin is that all of the states are at the same energy level, the ground state level, the lowest energy level. And if all the possibilities are that you're at that level, then you have a 100% chance that you're going to find your electrons there. And so when you go back to this equation and you plug in 1 for the total number of probabilities, well, the ln of 1 is 0. So automatically the entropy becomes 0. And so what Boltzmann kind of does with this equation, aside from giving us a link between the quantum world and the Newtonian microscopic world, is that, yes, take the temperature all the way to absolute 0 and the entropy of the perfectly crystalline system, which is technically the one addendum to it, is going to be 0, right? So this applies to crystalline substances specifically. It has to be a perfect crystal too, kind of like solar cells or solar panels have to have a perfect crystalline system, or else the quantum yield of the solar panels decreases considerably. Yes, the entropy of the perfectly crystalline substance will go to 0 because all of the electrons will be in the lowest energy state, and the probability of finding an electron will be 100% on that particular ground state. All right, now that's kind of the extent of what I want to tell you in regards to the third law of thermodynamics. If we try to go any deeper than that, this is going to get very complicated and confusing very quickly. So instead, I'll call it a day for the third law of thermodynamics, and now we're going to look at the second law of thermodynamics. Now, the second law of thermodynamics, once again, has to do with entropy. And the reason you haven't heard about the second and third law of thermodynamics until now is because you needed to know about entropy prior to talking about them. Now, the second law of thermodynamics it's a rather interesting and maybe to some degree almost philosophical way of thinking about energy. And the idea is that the entropy is going to equal the change in heat over temperature if the changes in heat that you are applying to your system are infinitesimally small. Traditionally, and most often than not, changes in heat are not going to be infinitesimally small. Sometimes the change in heat happens so fast that the idea of it, happening in small, tiny increments is just not realistic. So most often than not, the entropy ends up being larger than dq over t because the changes in heat happen so quickly for certain systems that it's just not a possibility to make it work out in infinitesimally small events. So what this basically then says is that because the changing entropy is going to be greater than dq dt, a reaction that is considered to be spontaneous, one that happens on its own, is going to have a total increase in entropy. The change in entropy will have to be positive for it to be um, a reaction that happened on its own. And by the way, when I say the total increase in entropy, I literally mean it. Because not only are we going to be looking at the entropy of the chemical reaction you're looking at, which we refer to as the entropy of the system, but we're also going to be looking at the entropy of everything else, which we refer to as the surroundings. Now this is where it gets a little bit philosophical, because technically speaking, and the names kind of imply it, the entropy of the system and the entropy of the surroundings is the entropy of everything. Therefore, we call this the entropy of the universe. And if the entropy of the universe increases, then you have a spontaneous reaction. If the entropy of the universe decreases, then the reaction you're looking at is not going to happen on its own. And for you to make it happen, you will have to do work on that system just to perform the task. All right, so this is kind of crazy though to think about, because it's like, all right, well, we barely we barely can, reach up, I guess, up until this point, the outer regions of our own solar system, with different probes. But, we cannot really reach every single extent of the universe. We can see some of it, but it takes a long period of time for us to observe things that are very far away from Earth. And so to think about the idea of calculating or being able to calculate the entropy of the surroundings directly, it's just not something that seems possible. But I'm going to show you a way in which we completely get around that problem. Now, before I do that, though, I want to give you another philosophical, not question, but kind of like prompt, which I think is actually rather beautiful. So if you think about the fact that we do live on Earth, right? We are technically organisms that are very well organized. We need our bodies and systems to be very well organized and on point about what they're doing. Otherwise, not only do we get sick, but we could potentially die if we deviate ever so slightly from the way the system ought to be working. So by all intents and purposes, human beings and other living organisms are very well organized, meaning that for us to exist, the changing entropy has to go down because we're more order than entropy will want us to be. And sometimes people kind of make the mistake of saying that, well, how do we even exist if the entropy is actually decreasing as a result of our systems being so ordered? And the thing that sometimes people fail to acknowledge is the fact that we are just a tiny, tiny little thing in the entire cosmos. And in fact, yes, there is, what, like 7 billion of us in this planet, and we are kind of order. But when you think about the scope of the universe, right, we live on Earth, which is a relatively small planet in one solar system, and the solar system is within the Milky Way, which has hundreds, if not thousands, of different solar systems within it. And so that alone creates a little bit of chaos, but the thing that really creates chaos is the explosion of a star. When a star reaches its end of its life, it explodes into a magnificent supernova, and that spews out elements and elementary particles and material all over into outer space in a very spectacular fashion that is of magnitudes that we can't even really like wrap our hands around. So the point being is that the entropy of such events is so large that having an orderly system like the human being alive doesn't remotely make a dent on how much entropy increase is happening from all the galactic events taking place in the entire universe. So overall, the entire entropy of the universe is greater than zero, is still spontaneous. So it's okay for us to exist. We're not violating the second law of thermodynamics by existing. In fact, if we were, we wouldn't exist, period. So we actually have not only ourselves, to be around and stuff, but we also get to enjoy, little bloggers like Popeye the Foodie, which has his own Instagram account. And nowadays he doesn't go to restaurants due to the pandemic, but if you check out his site, you'll see all the places he's being and all the foods that he's looked into. This is not my dog, by the way. This is just Popeye the Foodie. That's literally the title of his Instagram account. If you want to look at something cute. Anyway, so going back to this idea of the entropy of the universe, you can find the entropy of the system because technically speaking, that's the entropy of your reaction. And you could either use Hess's law to find the entropy of that reaction, or you could use the entropy of formation of reactants and products. But then the question becomes, how the heck do you find the entropy of the surroundings? That seems like an insurmountable task, a fool's errand, something that can't possibly be done. But I'm about to show you how you find these values by introducing yet a new player into the thermodynamic realm. So let's talk about the Gibbs free energy in the next video. I want to kind of leave you on this cliffhanger for this video so that you tune in to the next one. So see you in the next video.